Hello, welcome back. So, in this session, we'll start covering regression models. When it comes to machine learning, there are three different main pillars: regression, classification, and clustering. And for regression models, linear regression is a very basic but important model. There are a lot of core concepts that we can cover in linear regression, and those core concepts are equally applied to other machine learning models. So, linear regression is a method for predicting a continuous output variable. So, in our case, it would be stock price. So, we can use one or more input variables. As you can see on the right, we have number of users of that company, previous stock price, company revenue, and interest rate. We all know that these features somehow influence the stock price. So the core goal of linear regression is to find the best linear line that best fits our data. But the problem is, we're not sure how much each feature influences the stock price. So we need to figure out those specific numbers, which are indicated as alpha here. So we know that the previous stock price and company revenue would have a different relationship when it comes to stock price. So our goal is to find out those specific coefficients. And in order to specify that into a mathematical formula, we can say that the stock price is a certain function with company value. Let's say we have a stock price in the y-axis and company revenue in the x-axis. And those data points would indicate the stock price and the company revenue. And you can also see a red line there, and this would indicate the linear regression model that we currently have. However, even in plain eyes, it's pretty easy to tell that the red line doesn't represent the data that much. So in order to fit our linear regression line into the data, we need to figure out the appropriate slope. And in this case, we need to figure out the beta and alpha of that specific function. And one way to formulate this into a mathematical equation is to calculate the difference between the line and the data points. If you see the dotted line over there, the dotted line would indicate the difference between the actual data point and the linear regression line that we currently have. And we can see that the current linear regression line is not that accurate. As an example, when the company revenue is around 4, our linear regression line says that the stock price would be about 2.5. However, if you see the green line, which is the actual data set, it's around 10 or 7.5. So using these kind of logic, we can calculate the difference between the predicted value and the actual value that we currently have. And we can calculate this difference throughout all the data points that we currently have. And by calculating all of these, we can gradually fit our linear regression line to our data point. And to do this to all other data points in the graph, we can come up with the total error of this fitted line. And this fitted line could be represented as the mean squared error. The mean squared error is the total error term between our model and the data set. In very easy terms, if you look at the dotted line, it would indicate the difference between the actual and our model's prediction. So our total error would be the sum of all of those error terms. But mean squared error is a little bit different. The concept is similar, but a little bit different, and I'll tell you the specifics in the next slide. But one thing that we're sure is that a low mean squared error would mean that the model's predictions are closer to the actual values. And this means that the model is performing well. But if we have a high mean squared error, it would mean that the model is having a poor performance. And now, when we look into the specifics of our mean squared error term, we could see that it actually calculates the difference between the actual value and the predictive value. And after calculating the difference, we square the difference, and we do this for every single data point. And at the end, we calculate the average of all of these values. Then you might ask, why are we squaring all these differences? The answer is that we want to prevent cancellation. So, cancellation, if we just summed up all the raw differences, we have positive and negative errors. And those negative and positive errors can cancel each other out. And this could lead to misleading conclusions because we want to sum all of the error terms. And another effect of squaring the error term is emphasizing large errors. So being off by 2 is relatively less crucial than being off by, let's say, 10. So we want to capture these big differences in our error term so that our models can adapt accordingly. If we square 2, it would be 4, and if we square 10, it would be 100. Like this, we would like to capture big differences in our dataset. Now, based on the equation that we currently have, we can see some of the properties of this mean squared error. First, it's always non-negative. Since we square all the errors, it's always positive. And second, it emphasizes large errors, just like I mentioned. And third, it's sensitive to outliers. Because, as I just mentioned before about squaring 2 and squaring 10, the difference would increase dramatically. And this mean squared error term is used in many different machine learning algorithms, and especially in regression models. And now that we have calculated our mean squared error and know that our current model does not actually fit our dataset, we now need to move our linear line. We could see that most of the dots are above our linear regression line, so we can move our line upwards so that it fits well into our dataset. And if we move it upwards, and even after moving upwards, we can see that it does not fit our data as much as we want. And we're still not sure if it's the exact fit. Although it's definitely better than the last one, however, we also need to recalculate the mean squared error in order to quantify its fit to our dataset. Anyways, now that we know that lifting our line upwards fits better to our data, let's go for another iteration. Well, this time we have gone too far. The line way passes the data points that we have, and the error term rather increases. Then it's time to change our direction and pull down our linear regression model. And now, after a few iterations, we have the fitted regression model, and we could say that the total error term is at its minimum, and we now have a linear line that best represents our dataset. This whole process that we just went through is called gradient descent. So gradient descent is an optimization algorithm used to minimize functions by iteratively moving in the direction of steepest descent. And this is defined by the negative gradient. It's very widely used in machine learning and deep learning models, and it's mostly used to optimize those models as cost functions. Now, let's set aside all those difficult terms and go through exactly how it works step by step. So the gradient descent has 4 different steps. First, we initialize the parameters. Second, we compute the gradient. Third, we update the parameters of our linear regression model. And fourth, we check whether our model has converged or not. And after our model has converged, we stop this iterative process. So the first step is to initialize our parameters. We start with initial values for our linear regression model, And we're not sure about the exact coefficient values that fit best, that best fits our data, but we need to start somewhere. As an example, in our case, we tried to predict the stock price using company value, and we're not sure about the impact of company value having on stock price. It could be zero point 0.5, 0, or even 10. We're not sure. And even though we're not sure, we need to first set a random coefficient and start using these coefficients. So we first calculate the main difference, the mean squared error, to figure out how distant our linear regression model is. And after you have a guess for the parameters, you measure how good or bad that guess is by using a loss function. And this is a calculation of how far off your guess is from the target. And here the gradient is just a fancy term for the direction in which our current guess is off. So if you see the right side of our equation, you can see that we have a partial derivative function, and that is the partial derivative of our cost function, which is mean squared error. And if we take the partial derivative of our main mean squared error term, we can get a sense of the direction and the amount of error. So this gradient is something like a feedback. It tells you which direction to head to in order to reduce our error term. So without this, you won't know how to move your parameters or to get to a better result. And in math terms, we take partial derivatives of the loss function with respect to each parameter. So since in our case, we only have one parameter, which was the company revenue, but if we have many features, we would calculate these gradients for each and every individual features and and update the coefficients. Anyways, coming back, so the higher the error rate, the more we move our model. And if our cost function, which is MSE, is small, it would mean that our model needs little modification. And later on in the iteration, we will come to a point where our cost function or mean squared error term is small enough and we don't need to move our coefficients. If we visualize the steps that we just mentioned, it would look like the graph on the left. So we calculate the total error term in terms of company revenue. And now we need to update our model. We want to move our linear regression model line upwards, like the plot on the right. However, we're not sure how much we need to move. And in order to figure out how much to move, we need to calculate the learning rate. So from computing the gradient, we now know which direction to move and how much. However, we cannot use the whole error rate. We need to be able to move step by step since we're not sure whether our current move will increase the MSE or not. That's where we have the learning rate. The alpha symbol here indicates the learning rate, and the gradient we have computed is the partial derivative term on the right, and this is multiplied to the alpha. And this alpha, the learning rate, is a small multiplier, and it decides how big each step should be. If the step is too big, you might overshoot, and if it's too small, it'll take a long time to get to the right spot. Remember, the partial derivative of our cost function was the error term, and we want to decide how much of that error term we want to consider when updating our coefficients, and that is learning rate. And this is how our model learns. So with each update, you move closer and closer to the parameters that yields better results. So if you skip this process, our parameters will stay wrong and the model will never improve. Now, if the learning rate was too big, I just mentioned that it will overshoot, and you can see the result on the right. Rather than going to the right position on where all the data points are, it overshoot and goes over these data points. So the error term might also increase. So like this, it's important to find the appropriate learning rate. Now, coming back to our gradient descent, it's time to check whether our regression model converged or not. So, by convergence, it means to check, is our error as low as we can get, or are we barely improving? If changes to the parameters no longer meaningfully reduce the error, we can say that the process has converged. This means you're on the right spot. And usually, the algorithm would wait for a few iterations, maybe 5 or 10, to check whether our coefficient is updated in a meaningful manner. And the coefficient is not updated in a meaningful manner, it would mean that there are little or no space for improvement. So, as I mentioned in the 3 steps over there, it first keeps the coefficients where our cost function was its lowest, and it reiterates the optimization process and check whether these coefficients are updated. And if these coefficients are not updated for maybe a few iterations, it would stop the optimization process and we're in the right step. Now that we have gone through all the important concepts when it comes to linear regression, we could combine all these and build our model. The full code of our linear regression model would look like this. First, we have some parameters that we want to predefine. We have x, y, alpha, max epochs, and n and d. So x would be the input features. The y would be our target variable. In our case, it was the stock price. Max epochs means the number of iterations we want to perform our gradient descent. And n would be the number of samples, and d would be the number of features. In our case, we only had one feature, so it would be 1. And then we also want to initialize some of the weights and bias. If you remember, during the gradient descent process, the very first step was to initialize a random weight coefficient. So here the coefficient would be the weights and the bias. For linear regression, we have the intercept and the coefficients. Here the coefficients would be the weight and the intercept would be the bias. Now, if you see the code on the right, I have formulated a pseudocode that would perform a gradient descent. So first, we compute the predictions. And here we see the predicted y is a combination between x and weights and biases, our linear regression model. So after we get the predictions, we compute the error term. So the error term is the difference between the predicted and the actual values, and we calculate the gradients. The gradient would be the partial derivative of our error term, and then according to the derivatives, we update our parameters. And if you see the fourth step, which is updating the parameters, you can see that we need to update our weights and also our bias. And if it converges, and we would end the process. But one thing to point out here is that the error term here, I just mentioned that it's the difference between predicted y and the actual y, but in later process, we will use the mean squared error. Now that we have gone through all the basics of linear regression, and then it's time for us to build our model from scratch. We're going to use Python to build a linear regression model of our own, and after building our model, you would have a very comprehensive understanding of how regression models work. And I'll see you in the next session. Hello, and welcome back to the course. So in this part of the section, we are going to actually implement linear regression from scratch. So the reason we're implementing it ourselves is because we want to understand how linear regression actually works. And just importing a package and then running the results and then showing and interpreting the results won't help you that much because you won't be able to learn how linear regression actually works. So what we're going to do is we are going to use basic packages such as NumPy to create the linear regression model from scratch. And then based on these understandings, what you can do is it's going to help you understand how to tune the parameters, hyperparameters, and also these similar concepts or notions will be applied to other machine learning models too. So it's very important to understand how the very basic model, which is linear regression, works so that you can get a very good foundation and understanding of machine learning models. So let's begin by setting a kernel. So if you first go into a Jupyter notebook, you can use Visual VS Code or any other IDEs that you prefer. I'm currently using Visual Studio. And the first thing you can do is select kernel and then Python environments. And you can see some of the Python environments that I have created, but you can choose the one that you have created for this specific course. For me, I have created this from scratch environment. And then after clicking it, you can see that we have set our environment for this Jupyter notebook. So what it does in the back end is when running these kind of codes, we want to import some packages and necessary configurations. And we do this by setting and mapping our Jupyter notebook to a specific kernel or environment so that we can use the packages inside that environment. Now let's begin. So the very first step would be to import some packages. Here we are going to import this NumPy package, and then we are going to set a random seed. This random seed will be set to 125, 123. And the reason we set this seed is because we want to create some synthetic data. And when creating this data, we are going to create it in random. So this random seed would help us simulate the same results every time we execute this following function. Now, what we're going to do is we're going to create a synthetic data. And using our np-random function, we're going to create our input data set and our target variable. So for our input, we create a 101 shaped input. And if we print out x.shape, we can see that we have 101. And if we see the individual values here, we have the following values. And the way we're creating our target variable is that we are applying a certain function, a linear function to our target variable. The reason we're doing this is because we want our linear regression model to have an easy practice data set. So it will be a very easy data set for our linear regression model. And this is the overall structure of the linear regression model that we want to build from scratch. And if you have used scikit-learn packages at least once, you'll notice that most of the machine learning models there would have the same logic when training them or predicting the output. So it has the function fit and predict, and we're going to follow the same logic and implement the fit function and the predict function. And here we have the init function, which we will specify some of the parameters that we're going to use inside the linear function. And this fit function would train our data set train our model according to the data set and tune its coefficients and intercepts. And then this predict function will actually predict the output using the coefficients and intercept that we have trained. Now, what we're going to do is we're not going to implement this as a whole. What we're going to do is we are going to take a step-by-step process so that I can walk you through on how to implement these kind of models. So the very first step would be to initialize some of the parameters that we're going to use inside our model. So as we have discussed before, the linear regression model would have a few parameters that we can tune. As an example, the first one would be the learning rate, and then the number of iterations. So the learning rate will be the amount of updates that we want to apply to our coefficients according to our gradient descent. And then we also have number of iterations. This number of iterations would be the number of times we want to update our coefficients. And these other parameters would be used inside our linear regression model. Now, our linear regression model would look like this. We have the target variable, we have the intercept, and we have the coefficients and individual data sets. So the x are independent variables, which are the features that we put into, and then y would be the target. And using these function, we predict the output. And before putting the input data set into our function, our linear regression model, what we need to do is we need to reshape our input data. Our x data pretty much stays the same. We have the shape of 101, but our y, the target data, has to be reshaped because before it was 101 shaped array, but now we convert it into just a single array. Now, after we convert this, we need to understand how many samples and how many features that we need to train. As an example, if we print out on x.shape, we have 101. So this 100 would be the number of samples, and this 1 would be the number of features that we put into our dataset. So we only have one column to use as a training dataset. So we have 1 features, and this number of features would be used to set our coefficients because, my bad, we need to initialize our parameters. And then if we run it again, here you can see that we only have 1 coefficient. And the reason we're doing this is because based on the number of features, we need to understand how many coefficients we need to train. Because for every feature, there has to be a coefficient like this, beta 1, beta 2, etc. But for our case, we only have 1 column, and thus we only train 1 coefficient. And this, since we're not sure the specific number of the specific value of our coefficient, we initialize it using a 0. So that's why when we first, before training our linear regression model, our coefficient will be 0. And now the next process would be to iterate by the number of iterations here. And by going through this iteration, we want to update our coefficient. And here we want to update the parameters, but the way we update our parameters is by computing the gradients. So let me break this down step by step. So for every iteration, let's say we first predicted the y output, and here we have all zeros. And that's because for the first intercept, the first intercept is 0, and the coefficient is also 0. So whatever value you put in, whatever value you apply to this linear regression function, because the intercept and the coefficient is 0, the prediction will be 0. And because it's 0, the error term will be pretty big. So after predicting this, we compare our predicted value and our target value to calculate the error term. So here we have the error. And now we have calculated our error term. The next step would be to calculate the gradient. This is the code to calculate the gradient for our coefficients and intercept, but you don't need to go into the specifics. The only thing that you need to know is the gradient would indicate and provide us with the information about the direction and the amount of error that we have when comparing between the prediction and the true values. So this dw and db would indicate the gradient for our coefficients, and this would indicate the gradient for our intercept. Let me print this out for you to see what this looks like. So we have a minus 15 for our gradient of our coefficients, and for our intercept, we have minus 14. And the next step after calculating this gradient would be to decide how much of these gradient how much of this gradient we want to apply to our coefficient, and that would be the learning rate. So this learning rate is multiplied to our gradient in order to update our coefficient. So here we have set our learning rate to be 0.01. So if we apply this to our gradient of the coefficients, first we are going to have minus 0.15. And since our coefficient is 0, the new coefficient after one iteration would be minus 0.15. And in order to understand all of these, we are going to add all of these to our history list so that we can keep track of how our coefficient, intercepts, and also the mean squared error is calculated. Now, so after updating the parameters, we calculate the mean squared error, and this would be the difference. This would be based on the difference between our prediction and our Y target. And let's see how this goes after one iteration. So if we look at the history list, you can see that our coefficient and intercept is like this. And for our mean squared error term, we have 52. So this goes on multiple times, and here we set the number of iterations to be 100. Let's see if I'm correct. Yes, we have set it to 100, and this would go for 100 times. And now let's reinitiate the code so that it runs smoothly. And what you can see is that the mean squared error for the first iteration was 52, and the mean squared error for the last iteration was around 1. And by looking at this MSE history, you can see that our linear regression has fit into the dataset. And let's also check out the history. So here we have the intercept, and this is the coefficient. And after a few iterations, if we go to the very last one, you can see that our intercept has converged to around 3.39, and our coefficient has converged to around 3.46. If we go back to the very first code that we initiated, which was creating our synthetic data, you can see that we have applied a certain function to create our target variable. So here it's the linear regression. It looks similar to the linear regression model. It has the coefficients and the intercept, but we have put some noise into the data. But here the coefficient is 4 and the coefficient is 3 and the intercept is 4. And you can see that the output of our linear regression model it's not the same because we added some noise, but the values are pretty similar. And by looking at these coefficients, we can see that our linear regression model has a good fit to the dataset. And now we have created our linear regression model from scratch. You might have an overall concept of how it works, but a better way to grasp this inner workings of our machine learning model is to understand, to visualize all this training process. So that's what we're going to do. But first, I have implemented our function into this file over here, and it's under src models and linear regression.py. So we have the linear regression model that we have implemented so far. We have the fit function, we have the predict function, and the MSE function. So the only difference between the model that we have created together and this version of our model is that this new version would accept both NumPy's arrays and Python data frames. I've modified this so that it's easier for us to use. We don't want to convert every pandas data frames into a NumPy format. It will do automatically for you inside this function. And another small modification is we have the predict function and the MSE function. So this predict and MSE would be used inside this .fit function. Inside when calculating the gradient descent, we will predict and then we will also calculate the MSE. We have separated the function so that it's easier to use, and also we can reuse it somewhere else. And now going back to our notebook, let's import this model and fit our data set to our linear regression model. So if we print out the very last MSE of our training process, we can see that we have got the same result from the from scratch model that we have created together. And there are two parameters that we can tune using this when it comes to linear regression. So the first one would be the learning rate, and the second one would be the number of iterations. And we are going to see how, and by tuning this learning rate and number of iterations, we are going to see the inner workings of our linear regression model. And now this code was just made to visualize the output, so you don't need to understand line by line. You just need to look at the output, which is here. So if we execute this, you can see that as the number of iteration goes up, the total error term would decrease. These green dots are the data points that we currently have, and this red line would be the fitted line of our linear regression model. And currently the learning rate would be 0.01, and this dotted line is the error term between the actual values and our predicted values. So in the first few steps of iteration, you can see that this error term is very big. But as we iterate through the process, the total error term would decrease gradually, and then it will converge to a certain point. So this is how our linear regression model is fit into the data set that we currently have. But what if we tune or change this learning rate to maybe a smaller one, maybe 0.0001, which is very small? And if we print out the mean squared error term, you can see that the mean squared error term is pretty big. When it was 0.01, it was around 1, but now it's around 48. So the overall error term has increased, but let's look at the visualization and understand exactly what happens during the process. So here you can see that the overall process of updating our coefficient is very slow. Because our learning rate is very slow, even though we properly calculate the gradient, which is the direction and the amount of update that we need to take for every based on our error term, because the learning rate is too small, the amount of update that we apply to our coefficient and intercept is very small. So for every iteration, the update will be small. And since we only have around 100 iterations, it stopped before actually getting fit into the dataset that we currently have. So if we decrease the learning rate, it would mean that sometimes we would have to apply more iterations to our model for it to actually fit into the data set. And now let's modify it so that maybe we could go for 0.04. And you can see that the mean square error term is less than 1. So it has a very good fit. And let's see what happens inside this training process. So first, during the first iteration, it kind of overshoots. So our initial line was at 0, but after one iteration, it will, since the learning rate is pretty big, the update that was done on the coefficients and the intercept was too big. So it went over our data set. Then after the next iteration, it came back again and then goes up again. And after a few iterations, it converges into a certain point. So here what we see is that since our learning rate was big, we first overshoot and then we undershoot, overshoot, undershoot, and the amount of overshooting and undershooting would decrease gradually and then converge into a certain point that we want. And now we have seen multiple cases of our linear regression model getting fit into this model. And you can tweak the learning rate or you can tweak the number of iterations and see how the linear regression model gets fit into the data set. It's important for you to understand how gradient descent works. So I advise you to tweak some numbers here, tweak some values for the learning rate and the number of iterations to see how all of these gradient descent actually works. And since we have like a basic understanding of our linear regression model, what we're going to do in our next session is we're going to implement our from scratch model into a real data set and see how it actually performs. See you in the next session.